On the far side of the moon, in the Apollo crater, the China 6 lander and ascender, having completed the sampling mission, basked in the sunlight. A four-wheeled rover was mounted on the northwest side of the lander. We have already met it, when China 6 was still in the test building of Jinchan Space Launch Site.
At that time, we knew there would be a counterweight of about 5 kilograms, which would make the flight more stable.
Initially, it was developed as a counterweight resource. Without this small robot, it would just be a lump of iron.
This small robot measures 47 centimeters in length, 29 centimeters in width, and weighs about 4.5 kilograms, with 4 wheels each having a diameter of 23 centimeters. Although it is much smaller than the previous 2 Lunar rovers. It is China's first 5-kilogram class lunar surface autonomous intelligent robot, based on neural network artificial intelligence. It is named Jinchan. Suddenly, the rover was unlocked, and Jinchan sprang out instantly. The moon's gravity is only 1/6 of Earth's. So Jinchan became lighter on the moon, extending its vertical landing time. On the other hand, with the spring thrust remaining unchanged, the lighter Jinchan would be pushed farther. And its horizontal flight time would also be extended, resulting in a longer airborne time compared to ground tests.
The robot is symmetrical, with its wheels and body designed symmetrically, allowing it to move whether it is upside down or right side up. This is the first feature. The second feature is that its eyes or cameras are also symmetrical, meaning the front and rear cameras are symmetrical, allowing it to take photos regardless of its orientation.
After landing, Jinchan began to circle around on the lunar surface.
This is also a part of its design. By taking images of the lander and recognizing its position within the images, it could determine its own position relative to the lander.
The rover rotated and took photos, using the scenery in the photos to autonomously identify the lunar surface and the location of the detector. Once it recognized the detector, it moved away from it. The front camera was responsible for navigation, while the rear camera took photos of the lander and ascender. Jinchan moved about 20 meters to the northwest of the lander, found a suitable position, adjusted the framing, and captured this classic photo. The lander's mechanical arm was fully extended, as if to announce to the world that it had just made history by completing the first human sampling mission on the far side of the moon. Jinchan has initiated the practical application of embodied intelligent robots in deep space exploration, in future extraterrestrial exploration activities. Such robots that can autonomously explore the physical world and learn in a human-like manner to perform actions expected by humans may be more widely used. While China 6 was completing its sampling mission, the negative ions at the Lunar Surface Instrument and Detection of Outgassing Radon Instrument also functioned normally and obtained detection data. The 48-hour working time on the moon was about to end. On the morning of June 4th, people gathered early in Beijing Aerospace Flight Control Center Hall. The liftoff from the far side of the moon was a first for humanity.
Attention all stations, 1-minute preparation.
At this time, the orbiter and returner were flying in an orbit 200 kilometers above the lunar with an inclination of 138 degrees. Earlier, the support compartment had been jettisoned.
Jinchan reporting, the Ascender's 3,000 Newton engine ignited.
Engines started. The Ascender took off.
At 7:38 a.m., the Chang'e 6 ascender, carrying lunar samples, lifted off from the Apollo crater on the far side of the moon. Soon it turned to the northwest direction, and about 6 minutes later, entered a retrograde lunar orbit 210 kilometers above the lunar surface. To ensure the successful completion of the subsequent docking, the ascender's orbital plane had to match that of the orbiter. However, liftoff from the lunar surface introduced significant uncertainties. Chang'e 5 had lifted off from the near side of the moon, where 3 ground tracking stations on Earth could determine the trajectory of the ascender, ensuring it was on the same orbital plane as the orbiter. This was not possible for Chang'e 6, which lifted off from the far side of the moon. In Kashgar, western Xinjiang, the sun had not yet risen above the horizon at this time. The 35-meter antenna in Kashgar Deep Space Station was pointing at the crescent moon. At this moment, it could only rely on Chuechia 2 to track the ascender's liftoff arc.
The orbit of the ascender after liftoff was only a rough estimate. It was unknown whether it had entered orbit normally, if it was flying correctly, or if any anomalies had occurred during ascent.
Yet the trouble was still to come. The ascender had to move from the far side to the near side of the moon, and the 35-meter antenna had to switch from tracking the relay satellite more than 10,000 kilometers south of the lunar south pole, to the ascender emerging from the northeast direction of the moon.
There was a gap between the two targets. And during this time, there was a blind spot for ground control.
The accuracy of the ascender's orbit was uncertain, and there was a tracking blind spot. Could we capture the ascender?
Yeha detected the target.
In fact, the lunar surface liftoff process went smoothly, and the orbit was basically consistent with the pre-estimated one.
The first human liftoff from the far side of the moon was successful and on orbit. 2 days later, on June 6, the first day of the 5th lunar month in the Chinese calendar, the sun scorched the Earth. Viewing from the Earth, the outline of the moon completely disappeared in the sun's glare. For the near side of the moon, it was now shrouded in darkness. A round Earth hung in the sky. In the night sky, the Chang'e 6 orbiter and returner were chasing the ascender. The docking had to be completed in the shadows. The ascender was in a passive state, just flying forward. The orbiter was the active one. It gradually caught up with the ascender under the guidance of radar signals, and firmly grasped the ascender with 3 claws at last.
Sounds like an easy job. But it's actually very difficult to meet the control precision required by the claw-type low-impact docking mechanism. There is a Chinese saying, "half a bottle of water sloshes," which is somewhat similar to the problem the orbiter might face during the docking process.
The propellant in the orbiter's fuel tank was almost depleted. In the weightless state of the space, the sloshing liquid could cause the orbiter to sway as well. The 38 attitude control engines of various sizes were the busiest at this stage. They had to constantly sense and control the attitude to maintain stability.
As we approached within 100 meters and flew closer, frequent control maneuvers might interfere with the thrusters. This could lead to instability in the attitude.
There is a special device in the large laboratory of Shanghai Academy of Spaceflight Technology. It is a solid piece of granite. On the surface of the table, there are 2 levitating bases. After the test starts, the bases will spray gas from below, creating a 1 mm gap from the ground, allowing the bases to levitate.
In space engineering, the most difficult thing to simulate is the weightless state in space. The purpose of this table is to simulate the mechanical effects of docking in a weightless state in orbit at the smallest possible cost on Earth.
Yeha 4902, Chang'e 6 orbiter frequency switching completed.
At 1440 Beijing time, the two spacecrafts were only 100 meters apart. From the images taken by the orbiter, it appeared as if the ascender, in the dark sky, was a grayish-white object, similar to what a night vision device would capture. There was a bright spot on the top plate of the ascender, along with 6 bright dots, which were the targets. The orbiter calculated the distance between the two spacecrafts through image processing. The ascender was getting closer and closer.
Grab it now! Grab it! Grab it! Grab!
At 1448, the docking was completed. Next came the sample transfer. The returner's top cover opened, and the transfer mechanism's pawl extended, gripping the ratchet outside the sample container. This ingenious device utilized the principle of the instability of a parallelogram. Through 3 stretching and folding actions, the sample container could be transferred into the returner. At this critical moment, the video signal suddenly breaks up.
Yeha 4902 Chang'e 6 orbiter. Data transmission signal lost.
The signal is gone. Did something unexpected happen in the lunar orbit?
We stopped controlling the two spacecrafts. It had been determined that they had entered the capture zone, and we stopped controlling both spacecrafts.
After docking, although the two vehicles had formed a rigid connection, the orbiter still had some inertia. To ensure the stability of the combined vehicle's attitude control thrusters had to be used. Now, stopping control meant that the combined spacecraft would deviate or roll along the direction of the orbiter's inertia. The ground-directed antenna on the orbiter would no longer point to the Earth, thus resulting in signal loss. However, why should we stop the control?
Because in space, the force exerted by the claw mechanism holding the sample container was not very large. Activating the attitude control thrusters in this situation would introduce certain disturbances to the ascender or the orbiter.
It turned out that this stop was intentional. The purpose was to ensure that no other directional torques would be generated during the sample transfer process, affecting the operation of the claws. This gave us a deeper understanding of the guideline of China's aerospace industry: be rigorous and earnest, thorough and meticulous, safe and reliable, and ensure absolute success. At 1524, sample transfer was completed, attitude control resumed, and the video was transmitted back. Soon after, the ascender and docking frame, which had completed all tasks, separated from the orbiter and returner. It would land in a controlled manner on the far side of the Moon, between the landing sites of Chang'e 4 and Chang'e 6. The orbiter and returner had to wait in the lunar orbit for the right opportunity to embark on the journey back to Earth.
Digging and digging on the distant moon, bringing precious lunar soil back home.
Going home. Chang'e 6 is heading home.
Digging and digging in the lunar soil to see what's really on the moon.
Sudzhuang Banner, Inner Mongolia Autonomous Region, the Chang'e 5 returner, landed here in 2020. Unlike the previous icy and dark night, Chang'e 6 return time was in the scorching summer afternoon. On the morning of June 25, 2024, in a vacant lot on the outskirts of Hetian, Xinjiang, the rising sun shone on the satellite vehicle of Xi'an Satellite Control Center's mobile control station. When Chang'e 6 entered Chinese territory, the equipment here would first detect its trail. The Suzhuang Banner landing site's weather consultation concluded that it would be sunny with thin clouds in the afternoon. Under the blue sky and white clouds, a round-headed device, resembling a large surveillance camera, was already in place 50 meters away from the theoretical landing point. This was the landing site imagery monitor from the Jiuquan Satellite Launch Center. It had 7 identical siblings distributed around the theoretical landing area, tasked with videoing the returner from the moment its parachute opened until it landed. On a small hill to the south of the theoretical landing area, a 1-meter diameter optical telescope from Xi'an Satellite Control Center's mobile control station was on standby, pointing to the western horizon. The returner would emerge from the horizon at a speed of about 7 kilometers per second. From an altitude of 52 kilometers above the ground, to just before landing, the telescope had to track the entire process. To accurately track the returner, the operator usually practiced with aircraft in the sky.
2080.
Long focus, manual.
At 11 a.m., the ground search convoy set off. At 1:20 p.m., 5 helicopters took off in sequence. At this moment, the orbiter and returner were flying towards Earth at a speed of over 10 kilometers per second. At 1:22 p.m., at an altitude of about 5,000 kilometers above the South Atlantic sea level, the returner separated from the orbiter. After separation, the returner had to orbit the Earth for a short distance before landing. At 1:41 p.m., it entered the atmosphere at an altitude of 120 kilometers above the South Atlantic. As the altitude decreased and the atmospheric density increased, the frictional resistance grew larger. The bottom of the returner began to burn, with temperatures reaching over 2000 degrees Celsius. The high temperature caused the air molecules around the returner to gain enough energy for the electrons to break free from the atomic nuclei, becoming ionized. At this moment, the radio signal was blocked, and the returner entered the blackout area. It streaked across the sky of southern Africa, like a meteor. At 1:43 p.m., the returner flew over the Indian Ocean at an altitude of 63 kilometers above sea level. In the next 5 minutes, the returner's altitude would gradually increase. Many people say this is due to the ducks and drakes effect, where the returner bounced back from the atmosphere. Yet this statement is incorrect. The real reason is that the returner's speed was so fast that it directly penetrated the upper part of the atmosphere. During the penetration, the lowest altitude of the trajectory was 63 kilometers. At 1:48 p.m., at an altitude of 80 kilometers, air density decreased, and the returner exited the blackout area. 1 minute later, it entered Chinese airspace.
Initiate dual capture. Initiate scan.
Initiate scan.
Return to 0.
Dual capture completed.
Outpost dual capture completed.
Within 2.5 minutes, the returner reached the Taklamakan Desert. With an altitude of 96 kilometers and a speed reduced to about 7 kilometers per second, it would then head downward towards Suzhuang Banner.
Attention all stations, this is Beijing. The following is the first returner landing point forecast. The following is the second returner landing point forecast. The following is the third returner landing point forecast. The landing point coordinates are longitude 111 degrees 24 minutes 29 seconds east, latitude 42 degrees 21 minutes 32 seconds north. Beijing's third landing point forecast has been issued.
Along the return route, after data consolidation and calculation, the tracking stations provided 5 landing point forecasts for the helicopters and ground convoy. The returner proudly flew across the sky of our motherland, carrying the samples collected from the far side of the moon for the first time in human history. It is about to complete its mission. In the next part of its journey, it would burn again as it entered the blackout area for the second time.
Station 42 reporting. Target detected. Manual capture completed.
Copy.
Retriever 4 detected the target.
Retriever 4 detected the target.
Retriever 4 detected the target.
In the infrared band image of the 1-meter diameter telescope, the burning returner appeared as a bright white dot. It had exited the blackout area and was flying towards the landing area with a speed reduced to 6.4 kilometers per second. At 13:57:45, the returner ejected its parachute package. 12 seconds later, the parachute fully opened. Almost simultaneously, 8 landing site monitors also captured the parachute.
Beijing.
This is Beijing.
The communication equipment's optical pod has captured the returner descending smoothly. Over.
Copy.
At 14:03, the returner was about 3 kilometers above the ground.
Success was almost certain.
On the roadside.
At 14:07, the returner landed. Chang'e 6 achieved the first ever sample return from the far side of the moon in human history. This is another landmark achievement in building China into a space power, leaving a significant mark in the history of science.
Chang'e 6 success, new achievements made. Perfect success. China's space program, always a beacon of hope. China's search and rescue team, always a pillar of trust.
Soon after, the naming of the geographical entities near the Chang'e 6 landing site in the Apollo crater was officially approved by the International Astronomical Union. Another batch of Chinese names was added to the moon, including Shi Xiake, Li Bing, Zhang Zhongjing, Li Shizhen, Su Song, and Qian Xiongwu. The mountain to the south of the landing site was named Mount Song, and the landing site itself was named Statio Tianjiang. On June 26, the Chang'e 6 returner was transported back to Beijing. After half a year, it returned to its old home in Beijing Aerospace City. The sample container was taken out with extreme caution, and the weighing result was 1935.3 grams. On July 2, at the Lunar Sample Laboratory of National Astronomical Observatories, the lunar soil sample container was opened layer by layer inside the unsealing operation platform. In the sealed clean space filled with nitrogen, the surface collected lunar soil was scooped out.
To the naked eye, the lunar soil particles from the Chang'e 6 samples appeared lighter than those from Chang'e 5. With a less dark color, from a perspective of mineralogy, the Chang'e 6 lunar soil contained more feldspar than that of Chang'e 5. It contained more white minerals. I believe that the current landing site is an area where ejecta from various places are intermingled, with about 20% of the material being external ejecta.
The packaging of lunar soil was a meticulous task. First, the rocks mixed in the lunar soil were sorted out. The largest rock weighed 9 grams, and was about half the size of a thumb. Its main component was basalt. Upon closer inspection, there were also some components that looked like shiny glass. The core bags were cut into sections every 15 centimeters, to distinguish samples from different depths below the lunar surface. The Chang'e 6 mission entered the scientific research phase. In November 2024, Chinese scientists announced 2 research findings from the Chang'e 6 lunar soil. One revealed that volcanic activity existed at the Chang'e 6 landing site 2.8 billion years ago. The other study fulfilled academician Ouyang Ziyuan's expectation that magmatic activity on the far side of the moon had already existed 4.2 billion years ago. Humanity's understanding of the moon has taken another step forward. Looking back 20 years ago, Chinese lunar exploration program was officially launched. Over the past 2 decades, the planned layout of orbiting, landing, and sample returning have been steadily accomplished. 9 space launches, 4 lunar landings, and 3 Earth returns have all been successfully completed. Currently, 2 landers, 1 lunar rover, and 2 relay satellites are still functioning normally. This is unparalleled globally.
Over the past 20 years, each success has been achieved under the direct and correct leadership and strong support of the party and the state. General Secretary Xi has also pointed the way for us. Space exploration is a pioneering endeavor. Exploration not only drives technological development, but ultimately it must benefit humanity. Therefore, I believe that lunar exploration is a means, and application is the goal. We must contribute to the welfare of humanity.
The achievements of the Lunar Exploration Project are the culmination of the wisdom and hard work of several generations of Chinese aerospace workers. It reflects the significant achievements we have made in self-reliance and self-improvement in science and technology, and fully demonstrates the spirit, backbone, and confidence of the Chinese people. The exploration of space is endless. And China's lunar exploration will never stop. The Chang'e 7 and Chang'e 8 missions of the 4th phase of lunar exploration are already in development. In the near future, there will definitely be more probes from China landing on the moon.
前方崎岖路不平，苍凉的月球上留下你孤寂。